So, we are talking about theory of column. Last class we have completed the short column part. You must have remember we have divided a column in two groups. One is short column, another was long column. Short column part we have more or less completed. Long column, just what is the mode of failure, how it will behave under the load, what is buckling, all these things we are trying to explain. So, it was just the basic structural behavior of a long column. So, we will continue with that. Long column. Now, if we draw the diagram, what we draw in the last class, say there is a column like this, both ends supported. Now, the load deflection curve you must have remember delta, this was P. Now, there was a now, if it is a perfect system, so if you apply the load, it will directly take that load in the axial manner, there will be no lateral displacement. So, lateral, this delta is lateral displacement, right. So, if I draw the lateral displacement here, say maximum displacement if we try to define as delta. So, normally if the load at a lower range, there will be no delta. Now, it will come to a point P equal to P critical, then we will get the equilibrium as a neutral equilibrium stage. So, earlier it was a stable equilibrium. Now, at this level, if we give any displacement delta, so it will be there. Now, this value may be any value we can put here. It may be 1 millimeter, 2 millimeter, 3 millimeter, minus 5 millimeter. And if we cross that load level, when disturbance is not that, it will take care. But if there is any disturbance, naturally there will be a excessive deformation and the whole thing will fail. Now, this is the load deflection curve for absolutely a perfect column. Now, if I say the load is not acting at this point, so if I draw the column section here, so it is not at the centroid, it is little bit away. So, what will be happening? Load, if we shift, there will be load, there will be bending moment. Now, this bending moment will try to bend that member, plus the load part is there. So, automatically from the beginning, if we apply a P equal to very small value, there will be a small moment, there will be small deflection. So, if we increase the load, our moment is basically P into E. So, when we increase the load, moment part will increase, deformation will increase. So, if we have some, if we start from some imperfection here, or we got some curve like that. Now, the level of eccentricity or level of imperfection, if we increase, the curve will be much more flat type. If it is 0, it will try to shape like this. Now, our elementary theory, we assume our deformation is very large. very small, we are not taking it as large deformation problem. Now here, when the deformation is large, we can get a very small part of the curve. So if we try to get, because at this level curve will try to become flat, so at this range if we want to go, there will be huge deformation. So if we want to go to that range, we have to take the effect of large deformation, right. So whole problem will be a nonlinear problem, and solution of nonlinear problem is quite difficult. Now that here, if we just follow that curve, naturally we can take any small deformation. So this curve is valid for a small deformation as well as a large deformation. So with our small deformation, that type of problem we can handle, right. So up to this level we are in a position to handle a small deformation problem, and this curve there is no deformation, certainly there is a deformation. So here we can put small or large, and we have the capability, generally we can handle this type of problem, not the other type of problem. Other type of problem, definitely we have to have the understanding of large deformation problem, which is basically a nonlinear problem. Now if we try to study that problem, absolutely perfect case, then what will be the value of P critical, that we can determine from our calculation, right. Now before going for calculation of P critical for certain type of beams or certain type of, rather here column, not beam, I should mention one thing. Say there is a member, let me draw a member here. See, if we apply some load, so it will be under P some compressive force. Now the force can be applied in the form of, with some eccentricity, automatically moment will be there, or we can put some lateral load. Now here, due to Q, we will get some deflection, right. Say P is not there, due to Q we will get some deflection. Now if we add P, so what will be happening? Because P into that distance, that will give some additional moment. Due to the additional moment, there will be a further change in the deflection, right. Now due to the additional change, P into that additional change, it will generate second level of moment. So that will cause further deformation of the structure. So the entire problem, so if we try to follow what is happening, we are not getting a direct unique solution. The reason is very simple, the problem is not a linear problem. So earlier we have applied the method of superposition. Say beam, it is subjected to a number of load. The effect of all the load we have just simply algebraically added together to get the response, and we define that technique is method of superposition. Now here actually the problem or the structural element whatever I have drawn, this member is called beam column, because here there is a load. If P is not there, it is a beam. If Q is not there, P is there, so it is called column. When P, Q both are there, we say it is a beam column problem. Now beam column problem, the deflection estimation is absolutely nonlinear. So it is not linearly dependent on Q and P. Just I can give one example. Say Q equal to 1 Newton, P equal to 1 Newton. So if we get some deflection, if we make P, Q both double, deflection will not be double, it will be more than double, right. So here the phenomena is nonlinear for a beam column problem. Now beam column, at this moment we are not interested, we may be interested later, but here let us take a pure column problem under a compressive force, and we will assume everything is perfect, means cross section throughout the section is uniform, material property everywhere is same. There is no distortion or deformation within the member. So, it is absolutely perfect. Load is acting at the centroid of the cross section of the member. The supports are absolutely perfect. It is properly placed at the two ends. So, whole thing is in a perfect condition. We want to get the load P when we will get the critical load. Now, this problem we can take. This is one of the fundamental case. A column, it is hinge at both the end, right. Now, we can draw in a vertical member or we can draw in a horizontal manner also. So, if we draw in a horizontal manner, it is immaterial the way your now say the column is drawn in a horizontal manner. There is a load P acting from this side. This is hinged. Automatically there is a reaction force P will be there. So, entire member the P will be transmitted. So, everywhere it will be under P. Now, the length we can take it is L, right, and we can take the member cross sectional area is EI. We can pick up some axis system, say it is a Y, this is a X. Now, if we take the bending, it will be something like this. Okay. So, L is the length, EI is the cross flexural rigidity, this is hinged, that is roller, P is acting. So, bending is shown, XY is the coordinate. Now, when we will get bending? When it is P is below P critical, that bending will not be there because there is no transverse load. So, it should be either critical condition or above. Say critical part we are interested, above it will not be stable, right. So, we are talking about the three form of stability, right. So, without any there is no disturbance here, so it will be here, but if it is neutral, from here it can go to some other place, but here you can't keep it, right. Say it is something critical condition. So, if we give some displacement, it will be there. Now, if we apply load P, this end there will be a reaction P, right. So, the reaction you can say reaction will be also P. Any vertical reaction you will get in that case? There will be no vertical reaction because both the end are simply supported. So, there will be no moment there. Now, if there is a reaction here, it should be balanced by the opposite reaction because there is no applied load. So, if it is some R, it will be minus R. So, force part will be balanced, but they will create a moment. So, the moment on there is no applied moment. So, automatically those force should be equal to 0. So, from there we can get the idea that there will be no vertical reaction here. Now, if we take any section, say at a distance x, what will be the bending moment? Not, it will be 0. It will be P into Y, right. Say this is a typical section, it has a distance x. So, here the deflection is y. So, x y we have shown the axis system. The deflected curve, say it is represented by y is a function of x. The value is not known, but there will be some displacement here. So, this P into that distance, and that will be the moment.
This is after the deflection takes place.
After the deflection, when it is under deformed condition. So here what will be the moment? So there is no reaction here. So that reaction into that distance we are not getting, but this force into that distance we are getting some moment. Or we can just cut that section and take the left piece. Left piece, if there is a P, there should be a P, but there is a gap of P, the distance is Y, P into Y, that moment will be coming there. Okay. So in any form you try to investigate the problem, you will get a moment that is simply P into Y. And what will be the type of moment? Here it will be sagging type of moment. Alright. Now we have studied our moment curvature relationship. There we have seen it is minus EI d2y dx square, that is equal to your sagging moment, or we can say it is P into Y. Right. So EI is the flexural rigidity, d2y by dx square is curvature. So that should be equal to M, and we know if the moment is sagging type of moment with that type of sign convention. So here the curvature is negative curvature, right. So negative curvature means there will be a minus sign. If the moment is a reverse manner hogging type with that sign convention, the curvature should be positive. So here this should be positive. So that part we have discussed earlier. Now this equation, if we try to solve, so here we can write your d2y dx square plus p by ei y is equal to 0. So ei part if we put here, and both the term if we take on the same side, it will be like this, or it is defined in a much more, it will be k square y is equal to 0. But k is what? It is p by ei, right. So p by ei, square root is k, so p by ei will be k square, right. So that entire term was defined by a single quantity, but we have taken a square. So it is a matter of convenience, because later on when we will solve, we will find the square part will help us to represent some expression in a convenient manner. Now this is a very standard form of differential equation, d2y by dx square plus k square y equal to 0, right. Now we have to solve this equation, and from the solution we will try to get some idea about the critical value of the load. Now what will be the solution of that equation? So if we write the equation again, so it will be d2y dx square plus k square y, that is equal to 0. Now its solution will be, now this is what, first term is a derivative of y twice, and second term is y itself multiplied with a factor. So the solution will be such, if we take derivative twice, the type of expression will be same thing, only some constant part it will be coming out, and constant part we can adjust plus minus, and whole thing should be equal to 0, right. So one of the, say if we take y equal to some, say sin x, right, or so if you take derivative twice, sin will be cos sin, or if you take y equal to cos, cos will be sin cos. So if it is a sin cos type of thing, it will come back after taking derivative. Or sin cos, it has much more elegant form of representation is e to the power something, say e to the power x. E to the power x, if you take derivative, it will be e to the power x. Any number of derivative you take, it will be e to the power x. And e to the power x, if you expand, we can get sin, cos, sin hyperbolic, cos hyperbolic. So for that type of equation, the solution is y should be some constant e to the power mx, right. So, here this m and c, they are the constant quantity. So, main idea is if we put here e to the power mx will be e to the power mx after derivative. So, here you will get c m. So, the constant part we have to manipulate and get the actual solution, right. So, that is the basic mathematical tool, and the reason is coming from there, because if you take derivative you should get this term. So, if you substitute here, so what you will get if you take, so it will be m square c e to the power mx, right. So, c e to the power mx will be there. If you take derivative, c is a constant, e to the power mx from m will come first, second derivative another m will come, it will be basically m square plus k square and c e to the power mx, right. So, this is the part with that it is multiplied. So, this is the part after taking derivative m square is coming, or we can say m square plus k square c e to the power mx, that is equal to 0. Right. So, m square plus k square is c e to the power mx equal to 0. Now, from here this quantity should be equal to 0, either c will be 0 or this will be 0, this will not be always 0, right. So, x may vary. So, some e to the power something, if it is 0 also you will get 1. So, either c will be 0 or this will be 0. If c equal to 0, then we are taking y equal to 0. Now, that solution we know actually, if it is the load is within your P critical, there will be no y, no deflection. So, problem is solved, but we can say that is one of the solution. So, that solution we are not interested, we are interested in the other solution, other alternative is this should be 0. So, if that is 0, your m square plus k square equal to 0. Now, I was talking about why it was taken k square not k, because here there is a m square, otherwise m should be square root of this. So, that part is just simply avoided. So, we can write m square equal to, unfortunately it will be minus k square, and m should be plus minus, it is I key. I is what? Square root of minus 1, right. So, here I is square root of minus 1. Now, here minus came, so it will be under square, we have to take one imaginary parameter I, so that will be the thing. So, there are two possibility of m, one should be plus ik, another will be minus ik. So, what will be the solution? Y equal to c to the power mx. So, y will be, say one of the c value is a c1, so e to the power I k x, another value is c2 e to the power minus I k x, right. So, it is e to the power mx, m is ik minus ik. So, if we put ik, it will work, with minus ik also it will be working. So, we can say both will be there with c1 and c2. Right. Now, if we expand that, that should be c1 e to the power ikx can be written as cos kx plus I sin kx, and the c2 part we can write cos kx minus I sin kx, or we can write a cos kx b sin kx. So, we are getting two values of m, one is plus kx, another is minus kx. We have substituted here. Both may be there. So C might have a value C1 with plus, C2 with a minus. E to the power I kx, if we expand, its trigonometric expression is cos kx plus I sin x. If it is minus, cos kx minus I sin x. So this cos kx part, if you take common, so it will be C1 plus C2, that we are writing as a different constant, it is A. And sin kx part, say C1i minus C2i, that part we can write as B, right. So here we can write, say A equal to C1 plus C2 and B equal to C1 minus C2. So we can write in this form. So that is one of the standard form, or we are talking about the solution of this equation earlier, that y may be a cos x or y may be a sin x, right. So there also it will satisfy the equation. Now if cos x can satisfy that equation, sin x can also satisfy. So the total expression is in a general form, say A cos kx, B sin kx, right. Now there are two constant quantities, and these two constant quantities we have to find out from the boundary condition. So in deflection of beam, more or less you did the same thing. You have taken d2y by dx square is some moment, integrated, got some constant, substituted some boundary condition, and the constant you obtain. Now here what are the boundary conditions? So deflection is 0 at both the ends. So at x equal to 0, your y equal to 0, at x equal to L, your y equal to 0, right. So we come here, so I can show you the beam. So we have started with this beam. So at x equal to 0 and x equal to L, deflection will be 0. So we got y equal to A cos kx, B sin kx. Now if we put boundary condition, so at x equal to 0, y should be equal to 0. So if we put, so 0 will be A, cos 0 will be how much? 1, and B sin 0 will be 0. So if we put x equal to 0, it will be sin. So sin 0 equal to 0 and cos 0 is equal to 1. So from here we can write B is equal to 0, not B equal to 0, A equal to 0, because with B we are multiplying 0. Now if A equal to 0, your expression of y will be B sin kx, right. So the other boundary condition, if we put, say at x equal to L, y equal to 0, so y equal to 0, A already became 0, so there is no point of taking it. So it will be B sin KL. Right. Now with other boundary condition we are getting B sin KL equal to 0, or after this we got y equal to B sin Kx, because A became 0, second level we are getting it. So at x equal to L, it became B sin KL, y equal to 0. Now there are two possibilities. One is B is equal to 0, or sin KL equal to 0. Now if B equal to 0, so your equation will be y equal to B sin Kx. So B equal to 0 means y will be 0. So it is again that case, means y is basically your deflection of the beam. So deflection of the beam equal to 0. So that is the condition when load is within the critical range. So then y will be equal to 0. So that solution will get. Now other option, if b equal to something, it is non-zero quantity. Now sin KL should be equal to 0. If b equal to not 0, if b equal to 0, so entire solution will be 0. So that is the pre-buckling condition. Now we want to get something else. What is happening at least at the when the equilibrium is neutral equilibrium and the load is at the critical load level. Now there say b is not equal to 0 or y equal to b sin kx is there. So equation of the curve is b sin kx. So it will follow a sinusoidal curve having an amplitude b, and it will vary x equal to 0, 0, and other end it will be 0, it will vary something. So at critical range, if we give some displacement, it will take a sinusoidal form. So b if we give 1 centimeter, so with a 1 centimeter amplitude, we will get the deflected curve. Now during that condition, if b is not 0, then sin KL must be equal to 0, because that equation should be satisfied, the other boundary condition. So if sin KL equal to 0, KL will be how much? KL will be your n pi. So if n equal to 0, it will be 0. Say sin KL equal to 0. Say KL equal to some theta, sin theta equal to 0, theta, when theta will be 0, it will be at 180 degree, at pi, it will be at 2 pi, it will be at 3 pi, it will be at 4 pi. So n will be a multiplier, it may be 0, 1, 2, 3, 4. So if n equal to 0, again it is that basic case. So so it is entirely 0, right? But here we are interested, n should be at least 1, 2, 3, 4 some value. Now n, it may be 1, it may be 2, it may be 3, it may be 4, anything. It may be 0 also. 0 definitely we are not interested, because 0 again it will give that free buckling case. But normally this 1 is a very sensitive value. Now we got KL equal to n pi. Now if we write your KL equal to n pi, what is KL? If we take square of that, it will be k square L square equal to n square pi square. What is k square? P by I. So we can write P equal to n square pi square EI divided by L square. Right. So we got one deflected y equal to b sin kx, and KL for that case when b is not equal to 0, KL equal to n pi. So from there we are getting P equal to n square pi square EI by L square. Now if n equal to 0, so what will be the value of the load? 0. 0 means when there is no, it will be straight. No, but if n equal to 1, so P will be pi square EI by L square, right? Now if I draw the say beam part, if we draw again, right? Now it will be deforming like this, right? So y equal to b sin kx. Now your this k is your n pi by L. Now if n equal to 1, so k will be your pi by L. So if we put here y equal to say b sine, say from here, or in general form if we put n pi by L into x, right. So from here this k if we substitute, so it will be b sine n pi by L into x. So if n equal to 1, so it will be b sine pi x by L. So pi x by L, it is curve is like this. So when x equal to 0, it is 0. When x equal to L, it will be pi. When sine pi means 0, and when it is midway, so it is pi by 2 90, it will be maximum, and the value will be p equal to pi square ei by L square. Now if this is for n equal to 1, now if n equal to 2, your p will be pi square ei by L square, and here n square means there will be 4 coming here, and here n equal to 2 means it will be sine 2 pi L by x. So if we put L by 2, then this value will be L by 2, 2 cancel, it will be 0. So in that case, if I put the deflection equation, it will be 0, and it will be like this. So if n equal to 3, it will be like this, right. So here n equal to 2, n equal to 3, n equal to 1. So it is half of a sine curve. It is a full sine curve. It is we can say this is 1 and half of a sine curve. So if it deforms like this, we are going to get a value p equal to pi square ei by L square. If you want to deform in that manner, it will be pi square ei by L square into 4. If you deform like this, it will be pi square ei by L square into 9, right. So like that it will increase. So what will be the minimum value? So this is the minimum value, right. So this value is what? This is basically your critical load of buckling and the minimum critical load of buckling, and the different form of deflected shape, whatever I have shown here, we can say these are the mode of buckling, in which mode it will buckle. So this is, we say it is a first mode or the fundamental mode. This is the second mode, this is the third mode, like this. Now in normal case, if it is a perfect case, it will try to deflect or fail in the fundamental mode or first mode, because it will require less force, right. Now if you try to prevent here in fundamental mode, the middle part will undergo large deformation. Say there is a column, centrally there are some resistance, okay, there is a column, and due to the load it will try to buckle, and centrally somehow some member is passing, so it is preventing, okay, right. So there might be a little gap, not it is fully ensured, but anyway due to some physical constraint it can't undergo movement. So what will be happening? It will start buckle in the second mode, because here it can't, so automatically it will take that shape. In that case we will get 4 times the buckling load, okay. So it is n square, so n if it is 2, it will be 4, so buckling load will be increased. So we can say this part is represented like this, so this will be L by 2, so if I do L by 2 square, automatically 4 will go there, okay. So you can think in that manner, it is hinge here, or it is second mode, this is a support. So in any way, if you try to explain, you will get the value of the critical load. So sometimes this P we write P critical, so you can write P critical equal to pi square ei by L square. Now if there is no resistance, if it undergone a failure mode according to the fundamental mode, right. So for fundamental mode, that is the value, and these are the shape of your buckling modes, fine. Now this case we consider as one of the basic case or fundamental case, because it is a symmetrical case, both the end are hinge, and we are getting a nice expression pi square ei by L square, that is the critical load. Now we shall try to take different boundary condition, right. So not necessarily all the cases you will get a beam having both the ends simply supported. Now we will rather get different types of boundary condition. Now if I take a second category in the form of a cantilever type of column, say if I draw like this, alright. So we could draw in a horizontal way also, any here just I have drawn in a vertical manner. Say this side is your x and this side is y. We could keep the page in that manner also, no problem. Now due to that load, there should be a deformation like this, right. Now here this part is a delta. Now the load is applied. If it is beyond critical value, it will be straight. Now if it is a neutral value, if it is beyond neutral, definitely it will be interfailure. At least we can think the neutral case in a very theoretical manner. So if you apply the load, so it will be straight, but we can give little deflection and release, it will be there. So that is the situation. So delta is the tip deflection and it will follow a cantilever mode of deformation. Now we have xy, so at any point there will be bending moment. Now P will be shifted from here to here now. So initially it was straight, load was here, now shape is different, load is there. So at any station, so from x, what will be the moment? Say this is x, so this value will be y. So moment will be not p into y, here p into that distance will be the moment, right. So it will be p delta minus y, right. So your moment in that case, it will be p delta minus y. So here to here it is delta, this is y, so this part will be delta minus y. So p delta minus y, that part will be the moment here. Now that moment is giving a, say if we look from this side, it is giving a hogging type of moment, right. So or it will give a positive curvature. So slope is positive, that is increasing with x. So it will give a positive curvature. So we can write EI d2y dx square equal to your p delta minus y, right. Now this expression we can write, say EI part we can put below p, so p by EI we can express in the form of k square. So d2y dx square plus k square y is equal to your k square delta. The EI part you just put on the right side below p, so p by EI will be k square. So k square y minus that part, if you take this side it will be plus k square y, and here k square delta will be on the right side. Now if we try to compare with your earlier equation, we got d2y dx square plus k square y equal to 0, but here this side, right side is not 0. There is one quantity, it is k square delta, and it is a constant quantity, it is not a variable function of x or y. Now this is one of the standard form of differential equation. We say if the right part there is nothing, if it is 0, we say it is a homogeneous equation, right? And here the left part is identical with this, but there is something on the right. Now the y, it will have two component of solution. One is called a complementary solution and one is called your particular integral. Now what is complementary solution? See, if we make this part is equal to 0, so we will say it is a homogeneous part of that equation, right? So if we make it 0, so it will be the earlier equation. So what will be the solution? Y will be a cos kx plus b sin x. So if we put here, so what will be happening? This part will be 0 because 0 will be 0. Now there will be y particular part. If we put here, that part should be equal to y square delta, right? So it is just like integration constant. So if we integrate, we get some constant. That constant may have some value, it may have 0, depending on the boundary condition. Here also, this complementary condition, it may be 0 or some value, because this is the part, if we put this side, it is not going to affect the value on the other side, right? Because yc is coming by making it 0, and we have the solution yc will be your a cos plus b sin x. So here if we put, so a cos x will be a cos x with a minus and k square, and b cos x will be also b cos x with a minus and k square, and this side will be y square with a k square. So automatically it will cancel out, and cancel out means 0 will be equal to 0 this side, because equation will be satisfied. So this is one part of the equation. Plus there should be, if this is the part, left side will be equal to 0, it will not match with the right side. So there should be another part, and that part if we substitute, that will yield a value k square into delta, right? So right part we can say k square delta plus 0. For the 0 part, there will be complementary solution. For k square delta, there will be another part. Now you can say why we are taking it. Okay. I mean, there is a possibility. Okay. The value may be entirely 0 or it may be there. Okay. Now these are all mathematical, you can say we can follow strictly mathematics, or being an engineer sometimes I try to explain from physical side. Okay. That okay, this part may be 0 part. If it is 0, then there should be a solution. If there is something, if that part is there, at least that will not going to hamper. And y particular, that should be there to get some values which should be on the right side. Now that is called y particular. Now here this yc we are talking about, it is a cos kx plus b sin kx. So this part already we have derived for the earlier problem. So if you make right side equal to 0, so we will get the homogeneous component of that equation, and for that the solution is this. Now for finding out the yp, that particular integral, the treatment made is in this form. So we can write say this one, this is d square plus k square into y equal to k square delta. Now this y part we are taking common. So y, if we take common, it will be k square. If we take y common, it will be d2 by dx square. So this capital D is a operator. It is basically your d by dx.
That equation is writing in this form.
So that equation is written in this form. So it is y, if you take common, it will be this operator square plus k square y equal to k square delta. Now here we can write here y particular, right? It is a particular integral, or you can solve finally, you can take that as a contribution for the yp. Now what will be yp? So this part we can put on the other side. So yp will be your d square plus k square minus 1 k square delta. So d square plus k square whole to the power minus 1 k into k square delta. Okay. Now if I go to the next page, so just now we have written yp equal to d square plus k square delta. Now this to the power minus 1, right? Now here this is written in a convenient form. This k square part will take out. So it will be k square will be out and it will be minus 1, means k square will be there, and this side will be 1 d square plus k square minus 1, and it will be k square delta. And if we expand in a series this form, it will be 1 minus d square k square now what will be happening? Say we know a plus b to the power n. So it is a to the power n plus nc1 a to the power n minus 1 b. We write in this form. So here a to the power n nc1 n minus 1 b nc2 a n minus 2 b square. So it will go like this. So it will start with a to the power n, next a n minus 1 b to the power 1. So next gradually it will change. Now here if we, so 1 to the power something is always 1, and here first this will not occur, second term it will be nc1 is n is here minus 1, and this part will be there. So if you take this term, second term it will be d to the power 4 by k to the power 4. After that it will d to the power 6 k to the power 6. Now what is d? D is the differential operator. Now this side there is a constant quantity, right? So if we multiply, first of all this k square will cancel. Now it will be basically delta into 1. Second term if you take, so delta, if you take derivative twice, first derivative itself it will be 0, second derivative there is no way of getting any value, and if you take further terms, order of derivative is much higher. So all the term will contribute 0. So ultimately we will get y particular is equal to delta. So we can write the y equal to a cos kx b sin kx plus delta. So this part was complementary part, this part is the particular integral part. Now this is the solution of the cantilever beam. Now next we will put some boundary condition, find out a, b, from there we will try to find out the critical load, right. So in this class I am closing with that equation. Next class we will try to utilize, try to find a, b, critical load and all those. Okay.
1951. A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the NR Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future.
आदर्शाय मादर्शाय प्राणदास्मह्मयम् योगकर्मसु कौशलम् योगकर्मसु कौशलम् योगकर्मसु कौशलम्.
Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.